In this video, I want to talk through an example of a kinematic analysis of a situation that might be familiar to you. I want you to imagine a race between a Toyota Prius and a Tesla Model S. So they're both sitting at the stoplight and they're both ready to take off when the light turns green. I want to first, however, mention to you the reason why in a physics for health science class we spend time talking about races between cars, for example. Well, in this class we are learning the basics of physics, learning how to apply the fundamental principles of physics to some more or less, I guess you could say boring, but maybe a better word is pristine situations. For example, we want to learn about accelerations and velocities and forces and momentum and energy in kind of austere circumstances so you can learn the basic principles of physics. And then when you study physics in your discipline, then you're going to apply the basic principles to the situations that will be relevant for you. For example, if you're an audiologist, eventually you're going to learn about forces and accelerations of the eardrum, for example. Or you're going to learn about blood pressure if you're a pre-med or pre-PT or pre-physician's assistant. I can't think of all of the things you might end up studying, but my role in this is to teach you the basics of physics. So we're going to talk about a pretty simple situation that you probably have a good idea of the outcome. And again, if you imagine a Tesla Model S sitting at a stoplight next to a Prius, light turns green, they both go. Probably the picture you can paint in your mind of the result is pretty accurate. The Tesla will get off the line and end up going much faster in a shorter period of time than the Prius will. Well, if you look up online, you can find that a Prius, for example, is able to go from 0 to 60 miles per hour in about 10 seconds. The Tesla, however, takes about 5 seconds, or even faster in some models of the Tesla, to do the same change in speed. So we'd like to calculate the car's accelerations, which is a well-defined kinematic quantity. Acceleration is defined to be the change in velocity divided by the change in time. Now, if we want the acceleration to come out in reasonable units, we might want to deal with that 60 miles per hour first. We're going to tend to use units more often than not in the metric system, which would mean we'd like distances in meters and times in seconds. So in order to get an acceleration in those units, we're going to need that change in velocity in meters per second. So as a reminder, why don't we first turn that 60 miles per hour into meters per second? You could pause the video here to see if you can remember how to do it. But the idea is you start with the quantity that you're given, 60 miles per hour, and come up with a bunch of factors that will convert the miles into meters and the hours into seconds. I happen to know a couple of these off my head, top of my head. So the first thing we're going to do is convert miles into meters. We would want miles in the denominator because it appears in the numerator in the given quantity. And I happen to know that 1 mile is the same as 1,609 meters, give or take. So that would get the miles to meters. And if we stop there, we would have the speed in meters per hour. But we want to get the hours to seconds. So we need a factor that goes from hours to seconds, but this way around because we want the hours in the denominator of the given quantity to result in seconds. We want 1 hour is equal to 3,600 seconds. So you might want to calculate that out before I write the answer here, but you would take 60, multiply it by 1,609, divide it by 3,600, and you're going to end up with the final velocity in meters per second. I get 27 meters per second. So armed with the final velocity being 27 meters per second, and the initial velocity being equal to 0 meters per second, we can calculate the car's acceleration. Acceleration is defined to be change in velocity divided by change in time. But the main thing to keep in mind is that the way you're going to calculate the change in velocity is always to do the final velocity minus the initial velocity, v0 or v0. It's important to always do that this way because we're going to learn that sometimes acceleration comes out positive and sometimes acceleration comes out negative, because acceleration, like velocity, is a vector quantity, and pluses and minuses can infer direction. So in this case, the final velocity is 27 meters per second, and the initial velocity happens to be 0, because both cars start from rest. So if you want to get the acceleration of the Prius, then you take 27 meters per second, and you're going to divide it by the time it took to make that change, which was 10 seconds. So 27 divided by 10, 2.7. And the units are meters per second divided by seconds. Change in velocity, 27 meters per second, time, seconds. But rather than saying meters per second, which I really do like better, you could just write meters per second squared. Now, we have to also calculate the acceleration of the Tesla. It has the same change in velocity, but the time, instead of being 10 seconds, is only 5 seconds. So instead of dividing by 10, you divide by 5, and you end up with an acceleration which is like 5.4 meters per second squared. Acceleration actually is twice as great. So you're going to want to jot those numbers down because we're going to need them for the next part of this problem. The next part of the question that might be interesting to explore to try to visualize what's happening here is to ask ourselves, what is the distance that each car travels during this interval of time? You might think of it like this. They both have the same change in velocity, 0 to 60, but the Prius travels for 10 seconds to accomplish that change, while the Tesla only travels for 5 seconds. To me, that seems to be pretty clear indication that the Prius is going to travel much further to go from 0 to 60 than the Tesla will be. But we don't have to rely on our intuition in order to figure this out, because we have a formula that figures it out for us. The distance that something travels when it accelerates uniformly is equal to 1/2 at squared. Of course, that's providing that the initial velocity is equal to 0. So there is also a term v0t, which adds on to this if you look in the book, but since these cars start from rest, there is no v0t to worry about. We only need to calculate 1/2 at squared. Pretty straightforward calculation in this case. We're going to take 1/2 the acceleration. Let's do the Prius, 2.7 meters per second squared, and we got to multiply that by the time, which is 10 seconds squared. Don't forget the squared part. Now, what is the square attached to? Only the time, not the acceleration or the 1/2, but also the 10 seconds. So this 10 seconds squared is actually going to turn into 100 seconds squared. So you're going to have to do 100 times 2.7 and then divide the result by 2, and I end up with 135 meters. See where that came from? Now, we could take the time and convert that into feet, but if you roughly divide it by 3, you'd end up with feet. So it's not really all that far, maybe a little bit longer than a football field to go from 0 to 60. Now what if you're redoing the same thing for the Tesla? Well, instead of doing 2.7 meters per second, you would plug in 5.4 meters per second squared. And since that, and instead of plugging in 10, you got to plug in 5 seconds. So if you redo the calculation, to divide 25 times, I get 67.5, or around 68 meters per second. Let's round that up to 68 meters. So as we expected, the Tesla goes from 0 to 60 in 5 seconds, and that only takes 68 meters, which is something like 30 or 35 feet. Whereas the Prius, on the other hand, takes 135 meters, which is more than a football field, to accomplish the same change in velocity. So it's a pretty substantial difference. Now I do want to point something else here that might be useful to you to keep in mind. There's another way you could look at this. So each car starts from rest and ends with a final velocity which is equal to 27 meters per second. You might ask, what's the final velocity, or the average velocity of these cars? Well, it's only true when something starts from rest, but we're going to use this in lab, as a matter of fact, many times, that if something starts from rest and ends up going some final speed here, 27 meters per second, then the average speed or velocity of the car is equal to half the final velocity. If you want to think of it like this, for half the time the car is traveling, it's going slower than the average velocity, and for half the time the car is traveling, it's going faster than the average velocity. So if the velocity goes uniformly from 0 to 27 meters per second, the average velocity's got to be half that. So the average velocity for both cars is only 13.5 or 14 meters per second. So in this case, the average velocity, 13.5 meters per second. Now the reason why that's useful is that now we can pretty clearly see why the Prius goes farther than the Tesla. They both have the same average velocity. The Prius, however, average velocity of 13.5 meters per second for 10 seconds makes it go 135 meters. But for the Tesla, its average velocity also 13.5 meters per second, but since it's only traveling for 5 seconds, ends up only going half that distance, or 67 or 68 meters. So a bit tricky. If you're asked to compare the average velocities of these two cars over that interval of time, you would find in that instance that they're the same. So there's one other thing that I'd like to look at here, and that is, what do these circumstances look like if we make a velocity versus time graph? So we'd like to know if we were to visualize the car's velocity and how it changes over time, what would that look like on here? Well, if we assume that the cars accelerate uniformly, it means that their velocity versus time graphs will be straight lines. So let's take the case of the Prius, for example. It goes from 0 to 27 meters per second, but it takes 10 seconds to do that. So maybe about here. Let's see. I'm sorry, I'm having trouble drawing. Here we go. However, so let's label that for the Prius. Now the Tesla goes from 0 to 27, same change in velocity, but only 5 seconds. So that's the Tesla. And if we were to draw straight lines for these things, the Prius would follow that line, the Tesla would follow this line. So you can see that these slopes are different because the slope is equal to the acceleration. That's a main property that we learn in chapter 2. So the slope of the velocity versus time graph for the Tesla is greater than the slope of the velocity versus time graph for the Prius, because the slope is the acceleration. After all, how would you find the slope of this line? You would do change in y, that's change in velocity, divided by change in x. Remember, slope is rise over run, but change in x is time. So the definition of slope, rise over run, is the same as the definition of acceleration, delta v divided by delta t. We can do one last thing here. We can use this graph to imagine what would be the speed of the Tesla after 10 seconds. So imagine during this race, the Tesla got to 60 miles per hour in just 5 seconds, and the Prius, on the other hand, was only going around 12 meters per second. We might ask if we could extrapolate the Tesla's motion out to a time of 10 seconds, ask how fast is the Tesla going. So that's equivalent to saying, well, let's just continue this line. Let's extrapolate out to 10 seconds and find v. So I'd like to find the Tesla's speed when the time is 10 seconds. All right? Well, there's a formula for this, as it turns out. And that is that the velocity at some later period in time is equal to the starting velocity plus at. So that's a formula from the book. It comes from the equation for this line. The equation for this line is y equals mx plus b. So this is the equation of a straight line. It's just that in our particular case, the cars start from rest, or there's no y-intercept down here. So the final velocity of the Tesla after 10 seconds would be its acceleration, 5.4 meters per second squared, times the time that it was going. But if we're extrapolating out to find the time it takes to find, how fast it's going at 10 seconds, then 5.4 times 10 is 54 meters per second. Now, you could do the conversion backwards. You could convert this from meters per second back to miles per hour to figure out how fast that is, or you could just use some reasoning outside the box. If it accelerates uniformly and it's going 60 miles per hour after 5 seconds, it'll be going twice that after 10 seconds. And if you converted it out, you'd come out the same thing. So that's around 120 miles per hour. So this is an example of some basic ideas of kinematics from Chapter 2. So hopefully you take a look at this and try a few practice problems, and you'll catch the hang of it.